Hello, everyone. This is Elisa Baum. I'm GridGain Systems Director of Product Marketing. I'll begin in just a moment, but first I need to conduct a bit of housekeeping. Can you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? Thank you. I see hands. Great. Next, during this webinar, you will be on mute, but should you have any questions today, please enter them in the questions field within the control panel. At the end of the presentation, we'll take time to answer as many of those questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, I'll make sure that all of you have a link to both the recording and the presentation slides within 48 hours. So if you have to drop off, these things happen, you'll still get a link to the recording and the slides. I'd like to thank you for attending today's webinar, Distributed Acid Transactions in Apache Ignite. It's being presented by Akmal Chaudhri. He is GridGain Systems Technical Evangelist. And with that said, I'll turn the floor over to Akmal. Go ahead.
Thank you, Lisa.
No problem.
So, good morning, good afternoon, good evening. So wherever you are in the world, thank you very much for joining today. So I'm actually on London time, so it's just gone 7 p.m. for me. And welcome and thank you for joining and for giving your time today. So let me just switch this. And so I'll just say a little bit about my background then. So I'm a long-time IT guy, worked in a variety of different roles. Started life long time ago working as a developer, real-time systems, relational databases for Reuters here in London, actually. And then became an academic doing performance benchmarking for database systems. In those days, the late 1980s, early 1990s, it used to be object-oriented databases. That was the hot technology at the time. Subsequently left academia, became a consultant, working with clients on site and in-house, and technical architect. Subsequently worked for a couple of vendors, Computer Associates, IBM, Informix. Worked in the big data space sort of 2013 onwards as a technical instructor in the Hadoop area, and then a solutions architect in the NoSQL space, and then was an independent consultant for a couple of years before I joined GridGain to help them with Apache Ignite, to help promote the technology, to build the community, and to present at meetups and conferences. So as you can see, I've had a fairly varied career. And just to summarize then, so broad industry experience, worked with a range of technologies, obviously a strong focus on database systems, but also programming languages, did a lot of work with C++ during the 1980s, 1990s, subsequently Java. A lot of client-facing roles as well, particularly with some of the roles I previously held in terms of doing technical briefings and working with the academic community and developers. Publications and presentations too. So I was very fortunate in that I had the chance to work with a number of different colleagues over the years from the database space principally, and focusing on, as you can see from some of the titles there, object-oriented databases from a long time ago. Some of these books quite old now, and then XML database management sometime later. So I've had sort of plenty of experience working in different roles. So I think I consider myself very fortunate in having seen things from a variety of different perspectives. It gives you a great kind of outlook on life and the kind of problems and issues that different types of communities, different groups of people within industry face, whether you're looking at things from a developer's perspective, or you're looking at things from a manager's perspective, or you are a customer or a vendor. And that, I think, has given me, a very useful kind of insight and very valuable experience. Okay, so moving on then. In terms of the specific agenda today, I'd like to do a brief overview of Ignite transactions. We'll look at concurrency modes. We'll spend a bit of time on two-phase commit, as that's the sort of main thing that we sort of focus on with Ignite. However, Ignite does offer one-phase commit optimization, which is kind of useful in some situations, and we'll briefly talk about that as well. We'll talk a little bit about RAM and disk level consistency and how to handle deadlocks. Okay, very important subject, whether you decide to go with the transactions or you don't want to use transactions. There are a variety of ways that you can manage this. Have some demos as well. Hopefully we'll be able to get through those fairly quickly, and then Q&A at the end. Okay, so ACID transactions still very important for many applications today. Often we need a single source of truth, and then ACID gives us very strong kind of guarantees. And this is very, very useful, particularly for Apache Ignite. Now, obviously, Ignite is a distributed system and supports distributed transactions. There is a strong focus on standards. And if you look at many of the standards within the Java space, for example, that Ignite follows those. And one of those is the Java Transactions API. So if you're familiar with that and you know how things work there, then you'll know the value that that brings. Used by financial institutions. So we specifically mentioned financial to highlight the fact that often requirements in this space are quite stringent. This community tends to deal with huge amounts of data, and often reliability and confidence in the technology is very essential. So, that is a kind of major user of Apache Ignite, and obviously its sort of commercial offering as well from GridGain. Atomicity modes, atomic and transactional. Okay, so we'll discuss this in a little bit more detail coming up next. Okay, so atomic mode. So very useful in situations where we want to apply updates straight away, and where we're dealing with kind of individual cases where we want to do a kind of a put into an Ignite cache. Very straightforward. We don't acquire any locks, and therefore we get much, much better performance. Transactional mode is much better, where we need to group together multiple operations, and we need to ensure that these are all done together, or they're rolled back if there is some failure, or none of them are done at all. I mean, this is where this whole issue of ACID compliance, atomicity, consistency, isolation, durability, operations are atomic. There's consistency, so we're changing the state of the system from one consistent level to another consistent level. Again, this single source of truth that we need to ensure that operations are isolated and they are durable as well. And we'll look at durability particularly later on, where in fact, although Ignite focuses very much on cache and holding things within memory, there is now a persistent store that comes as part of this. And obviously there is integration as well with third-party systems, whether that happens to be a relational database, a Hadoop, or a NoSQL system, or some other type of durable sort of system that we may want to save our data to. More about that later. Very briefly then, so concurrency modes and isolation levels. So we've got two types of concurrency modes, pessimistic, optimistic. So those of you who've worked in some of the areas such as computer-aided design, computer-aided manufacturing, for example, you'll know that typically in those kind of environments where a designer may be working on some part of a design, typically they'll check that out. And generally that's under kind of optimistic control. You're confident that you're not going to be interfering with somebody else's work. That sort of area of design that you are working on, you are responsible for that. Typically you'll check that out, load it into your local workstation, you'll work on that, and then be able to check that back in at some time later. And generally there's no concerns there. With pessimistic, we need to ensure, and this is where sort of the issue of locks comes in as well, that typically there we focus on locking. We acquire them. They may be acquired during the first read or write access. In the case of Ignite, we may acquire them in a primary node first and then promote them to backup nodes during sort of the prepare stage, for example. The order of locks is important as well. Apache Ignite will acquire locks sequentially and exactly in the order provided by a user. So very, very sort of important and relevant there. More about this a little bit later on. In terms of optimistic then, as far as Ignite is concerned, so entry-level locks are acquired on primary nodes during the prepare step, then promoted to backup nodes and released once a transaction is committed, okay? And we'll talk a little bit more about this sort of prepare and commit very, very shortly, okay? You'll get to see a little bit more of this diagrammatically and graphically what we are doing here. Locks are never acquired if a transaction is rolled back by the user and no commit attempt was made. Typically in this environment as well, so the key order is important. And we'll talk a little bit more about read committed, repeatable read, and serializable. And you'll see this in some of the code examples we'll do a little bit later on. So we have a number of sort of choices. So in the case of a pessimistic concurrency mode with an isolation, say read committed, we don't take a lock out at the time we read something, but we do apply a lock at the time we write something. With repeatable read, for example, we're able to cache some data locally, so we don't have to go back and reread it. And serializable is important as well, because we want to ensure that if we've got multiple kind of operations, they are interleaved in some way, that it's as though we were able to do these one after another. So we need to ensure that updates are not lost, that the correct operations are applied, and again, our system is consistent from one state to another. The nice thing as far as Ignite is concerned, this combination of pessimistic, optimistic, plus the 3 isolation levels, you can have all combinations of these, and these can all be used simultaneously. I mean, this gives you a great deal of flexibility. On the right-hand side there, you've got a very simple example of some Java code there. So you can see that we've got sort of a transaction being defined there. We have a start, tx start at the top there within the try line. And then towards the end, we have a commit. And within the middle there, we've got some update or some modifications that we're doing to some data. We've got no exceptions being trapped here, but again, we'll look at some examples a little bit later on to see how we can deal with some problems that may occur if that transaction is unable to commit. What can we do? You know, how can we trap that? How can we see what is the problem that's being caused? And if necessary, we may need to retry that transaction again to ensure that it's complete successfully. Okay, so here's an example of a pessimistic transaction, very sort of simple piece of code. Now, as you can see here, I mentioned previously that we can combine the repeatable read. If I just go back here, the read committed, the serializable with either pessimistic or optimistic. And so here in this particular example, we've got a transaction where we are starting pessimistic mode with repeatable read. So again, we're performing some action here. In this case, we've got some account information. There's an ID that we're getting from the cache. We are depositing some money, updating the value of that. And again, we've got some code examples later on to show this. And then we're writing this back into the cache. And then we're just committing this operation. Again, no sort of information further down in terms of how to deal with exceptions, but we'll look at that very shortly. In terms of optimistic, well, we're generally kind of hoping that we aren't going to experience any problems. So here we've got an example where the concurrency mode is optimistic and the isolation level is serializable. Again, you can see that this is a valid combination. Very similar to the previous example in terms of getting some information about an account, and we want to be able to update some value in terms of the balance of that account. We write that back, we try a commit, but in this case, we may have a problem, okay? Because this is optimistic, it's highly likely if this is a very kind of, you know, in terms of concurrency, there's a lot of other operations going on that we may not be able to update this particular account. We can try and catch that and retry this. So this is why we've got this code, rather than just having a standard try-catch block. You can see now right on the outer sort of boundaries of this, it's all contained within a while loop. And then just after the tx.commit, you'll see that there's a break. So in the event that the transaction committed successfully, that's okay. It will go to the next line, it will break from the loop, and it's been successful. In the event there was some problem, it will retry again, hence the while loop, okay? So it will make another attempt to try this. And again, the code examples later will demonstrate how this actually works. Okay, so one of the things that we need to be aware of is sort of, you know, some performance considerations particularly when we're thinking about transactions. So suppose then we've got a cluster with 3 nodes here, node A, node B, and node C. And in a transaction, we are trying to do a put operation, okay? So we want to be able to write something to each of these nodes. And then we've got some values that we want to write, sort of 1, 2, 3, 4, 5, 6. Okay, so the keys, the way that they are mapped in this particular example, we can see that keys 1 and 4 are mapped to node A, 2 and 5 are mapped to node B, and 3 and 6 are mapped to node C. So in pessimistic mode, Ignite cannot rearrange the lock acquisition order. So it'll have to make 6 sequential network round trips. Okay, it'll have to do them one at a time. So it'll do ABC and then ABC again. So in the case when the key locking order isn't important, it's better to kind of group these keys together. It saves sort of network time because there's less work to do. And the lock keys within the same partition together. Okay, so this can reduce the number of network messages. In this example, then, assuming that we've got this particular mapping, we can do 1 and 4 together, we can do 2 and 5 together, and we can do 3 and 6 together. So what we have is this kind of scenario where rather than 6 operations, now we've reduced it to 3. So 3 sort of round trips is a lot better in this situation. Okay, so there's sometimes we need to think carefully about this, and in performance considerations, simply realizing how we can do this type of mapping and in terms of grouping the keys in some way could be very valuable and help in terms of reducing the amount of time that's needed, as well as the number of operations that may be needed. Okay, so a little bit more about this. So two-phase commit protocol then, so there's 2 phases to it, exactly as on the tin. So phase 1 is a kind of prepare phase. Okay, so the 2PC protocol is initiated when an application has made a decision to commit a transaction. So in this case, the coordinator, which is our application, sends a prepare message to all of the participating nodes. And here we can see we've got primary nodes and backup nodes. So the message, the prepare goes to the primaries. Primaries send the prepare message to the backup copies, and everyone acquires their locks. Once the prepare message has, everybody has received it, everyone's got and said, yes, we're ready, then we can do a commit. Okay, so we can see this here. Very straightforward. Okay, now there's certain scenarios and situations that may occur, so we can envisage some problems here. What happens, for example, if we lose a primary? What happens if a backup goes down? And in the worst case scenario, what happens if we lose the coordinator, or a combination of those where we may lose a coordinator, a primary copy, and a backup copy? And these are the kind of situations that we'll look at over the next couple of slides to see what, how would Ignite sort of deal with these kind of situations. Okay. Now, one of the things that we need to remember, particularly with Apache Ignite, is that because it's in-memory only processing, this gives us certain benefits as well. So we don't need anything more complex than two-phase commit. There are some systems, for example, where we may have to go to 3-phase commit because we're dealing with a durable system. We're trying to save to a database system, where we're trying to save to a state beyond what's held in memory. That's okay. I mean, the thing is that with Ignite, we've got certain benefits. Because memory is volatile, we don't have to worry about the fact that, if the system crashes, the 2-phase commit is enough for this. The other issue is that we may be dealing with some level of persistence as well. So we may, for example, be reading and writing from the Ignite persistence store, or some kind of third-party persistence. Could be a relational database, for example, NoSQL, something else. In some cases, we need to think carefully about what's the behavior in those environments. And again, we've got some graphical sort of images a little bit later on to show you how we deal with the situation where we've got, for example, a relational database. Okay, so here's a case where we've lost a backup. So if the backup fails during either the prepare or the commit phase, then no special handling is required. Okay, so the data will still be committed on the nodes that are alive. Okay, so in this case, we've lost a couple of backups, but that's okay. Ignite will designate a new backup node, and the data will be copied there. outside of the transaction scope. It's self-healing, okay? So it will take care of itself. This is a sort of fairly easy situation to deal with. How about the situation there when we are losing the primary, for example? So in this case, what will happen is that during the commit phase, oh, let me just move on here. Okay. Backup nodes will detect the crash and send a message to the coordinator to find out whether to commit or roll back. Okay. So the system will be rebalanced. Again, it's self-healing. Coordinator will complete the transactions and then promote a backup to the primary. So this is the sort of situation where we lose the primary. So previously, it's less of a problem. Okay, simply we've lost the primary. Ignite will realize this. The backup there, and I apologize, I don't have sort of fancy animation to show this, but the backup has become the primary there. And again, it's self-healing. It's taken care of itself. And then a new backup can be assigned a little bit later on. So in this scenario, we've lost the primary. The backups can contact the coordinator, to ask, should we commit or should we roll back? What should we do in this sort of situation? In the case where we've lost a lot more than just a couple of backups or a primary, or in the sort of worst case scenario where the coordinator itself has gone down. So without the coordinator node, we can't do very much. I mean, neither the primary nor the backup node know whether to commit or to roll back. So in this case, for example, we initiate something called the recovery protocol. All the nodes participating in the transaction send a message to every other participating node, which we can see here. Okay, so we've got a couple of backups there sending a message to each other, and we've got the backups contacting the primary that's still alive here, and requesting what's actually going on. If at least one of the nodes here replies no, okay, then the transaction will be rolled back. Otherwise, the transaction will be committed, okay? So in this particular case, again, there is a way to be able to recover the situation, even though it looks quite dire. Moving on, we've got something called a one-phase commit optimization, okay? So this is very useful in certain scenarios where, for example, we have the situation with one primary and one backup. And that's quite a common sort of case in many deployments for distributed caches. If you add more than sort of one backup copy, say you've got two, then you'll have to revert back to the two-phase commit as previously discussed. So this is quite good. It minimizes cluster nodes in a transaction, okay, because now you're only dealing with one backup. All transaction entries belong to the same partition, okay? Backup copies will also be grouped together. That gives us the benefit in terms of where the backup data is held as well. And we may use some type of mapping in order to group that data together. For example, we may wish to hold all particular employee data that's related to a company on one particular node. That could be a very useful way to deal with this type of scenario where there is some type of affinity between the data, and therefore when we apply some operations, we are sure that we only need to go to one primary, and then if there is some backup data held as well, again, it kind of mirrors this in terms of the grouping of the data. So we can experience some similar sort of problems here. So what is the case here? Well, the ideal case here is then again, we've got a coordinator. Now you'll notice here that our keys 1, 4, and 7 map to the same partition in that they are held on the primary. They are held locally, okay? So there isn't any need to go elsewhere to be able to find that data. The client node sends the complete transaction logic to the primary. Okay, this is possible because we ensure in advance that all keys are mapped to the same partition on that node, which we mentioned in the previous slide. So once the primary receives that transaction logic, it acquires all the locks locally, which we can see here. So we can see there's a lock key 1, lock key 4, lock key 7. Once the primary receives the transaction logic, it will acquire all the locks. It will send only one commit to the backup. Okay. The backup acknowledges the commit. The commit is performed on the primary, and then the primary sends an acknowledgement back to the coordinator. So this is the kind of ideal situation. Now, again, we can have a number of sort of scenarios here in terms of failure of primary, backup, and so on. Excuse me. So in this case, so if we lose the primary before it's able to send the commit to the backup, then actually it's okay. There's been no changes on the backup. There's no side effects, okay? So there's nothing further to do here. This is okay. This situation is okay. There's no particular problems as far as this one is concerned. If we go a little bit further in terms of how much work has been done, so if the primary fails, after or during the commit acknowledgement is received from the backup, then the backup transaction is committed. Data are consistent on the backup, but of course the primary is down, and therefore there needs to be some communication between the coordinator and the backup to ensure whether that commit was actually completed. At some point the primary will come back up again, and then we need to apply some transaction logic there as well. We've got the notion of a recovery protocol here as well. So this is very useful in the sense that if the primary was able to send the acknowledgement to the client, that's okay. If it can't, we can see the scenario here where the work has been done, the primary has acquired the locks, the commit has been done to the backup, the acknowledgement from the backup has come back, the primary has committed as well, but we've got a failure after that point. So we're not quite sure whether, and certainly as far as the coordinator is concerned, doesn't know whether data that was committed on the primary. So again, this recovery protocol that we discussed sort of previously, that's kind of initiated to take care of this situation. Okay, one of the nice things about Ignite is the ability that you can store data both in RAM and on disk. ACID compliance is supported on all these levels. So both within what's held in memory and what's stored on disk in terms of sort of long-term durability. We can expand the two-phase commit protocol to the disk as well. And there's a couple of options that we have. So one of the ways that we can store things into disk sort of more permanently rather than holding it in cache is to use the Ignite persistent store. So we need to look at what sort of, in terms of durability and consistency support is available there. The other issue is what about things like third-party stores then? So typically in this scenario, we need some kind of transaction control, okay? And we need something like a relational system, I think, is the best fit. And again, we'll talk about why that is in just a moment. So this is the new kind of durable memory architecture that has been recently promoted with Ignite. So we've got this notion of memory split into regions, regions are split into segments, segments split into pages, and then we can see that the pages hold particular types of data. It could be data, it could be metadata, data about data, or it could be indexes themselves. And there's a sort of fair amount of information around this that's been published recently. So this is the approach that Ignite uses. Drilling down a little bit more and then looking at this. So what we have here is as mentioned previously, the ability to expand ACID compliance to the disk store. Ignite integrates with a lot of sort of external sort of sources such as SSDs, flash, for example. There is SQL 99 support, and we can perform operations both on RAM and what's stored on the disk. So there's a subset of the data that's held within RAM. We can perform the joins, all of these type of SQL operations, both within what's held in memory and what's held on disk. One of the things that Ignite offers is this notion of a write-ahead log, okay? Because this is what gives us the sort of recovery and helps us to, when there are issues in terms of loss of a part of the system or a particular node goes down. One of the nice benefits about this as well, that we get this kind of instantaneous restarts, because it stores a lot of this information. The Writeahead log gives us the ability to do recovery as well. And specifically, if we look at this in a bit more detail then, so what we have, if you look on the right-hand side, then this sort of stage one, once a cluster node receives an update request, it will look up a data page in RAM where the value is to be inserted or updated. The page will be updated and marked as dirty. It's changed, that some values have changed on there. Secondly, the update is appended to this Writeahead log, which I previously mentioned. Okay, so this, what it's propagated, it gives us this kind of recovery mechanism in case things go wrong. In terms of the next step, then sort of point 3, the node sends an acknowledgement to the update initiator confirming the success of the operation. And then finally, there's this sort of checkpointing that's done as well periodically. So with this Writeahead log, we get the ability to have fast performance because the changes are written to the log. Periodically, the log is sort of trimmed down, okay? So the changes are written out. Otherwise, this log would just grow continuously, and then that helps in terms of reducing the size of the log. And where the changes are in memory and these pages have been written to disk, again, once those updates have been done, you know, we're reducing the size of this log file. How about things, sort of situations where we're dealing with something that isn't managed by Ignite, things like third-party stores, for example. So we may have a situation, for example, where the coordinator, you know, we have a relational database, for example, which is why we need this kind of transactional control, because typically the majority of relational systems come with strong transaction support. If you look at the world of database management today, then many of these NoSQL products, for example, they have things like eventual consistency, and you know, the guarantees are very different from the sort of ACID compliant products that we see typically in relational systems. Now, this is important for a reason, which we can sort of see on the next slide here. So as far as the 2PC protocol is concerned, remember we have the prepare stage and the commit stage. So coordinator will have to write the transactional changes to the database before it sends the commit. We can't tell whether the database had committed or not. So what we can do then is we ensure that the operation is applied first to the database system. We, you know, that is our sort of single source of truth, if you like. And then subsequently, we apply the commits to the primary and the backup copies. Now, in the event that there's some sort of problem here, we lose a primary or we lose a backup, or in the case, this particular scenario where it's even more serious than that, then we just simply reload from the database system. That is our kind of single source of truth, if you like. Okay, so how to deal with deadlocks then? So there is some mechanisms built into Ignite that help prevent distributed deadlocks, okay? And we'll look at the code examples very shortly to see how these actually work. What this can do is, particularly when, you know, if we have this as part of a try-catch block, we can trap the exception, we can print messages out, we can get more details about what the actual problem is, and that will help us in terms of avoidance and debugging. That was very sort of useful features. There is other cases where we can run deadlock-free transactions. So these tend to be optimistic. So we're hoping that there aren't going to be any problems. If there are, we can retry. Okay, we can retry a particular transaction. Again, the code examples will demonstrate how this actually works. Okay. Okay, so let me just switch now to a couple of demos then, and then see how these might work. Okay, so the reason I'm running this inside VMware is, unfortunately, I tend to break my laptop rather too often through installing and uninstalling things. So part of the reason here is at least the environment is a little bit controlled. And what I would say to you is that certainly as far as these code examples go, let me just point out where they are. So if you can see this, okay, so if you go into GitHub, and look at Dennis Magda's, D. Magda's account, you drill down a little bit. As you can see here, you need to go down a sort of few levels. You will find these Ignite transactions examples there. So an example of how to do a pessimistic transaction, deadlock-free transaction, and deadlock detection example as well. So if we have a look at this first one, which is the pessimistic transaction example. So let me just close this window here, and we can have a look at this code in a little bit more detail. So let me try and just scroll here a little bit. Okay, so in this particular example, very, very simple. So we've got the fact that it's transactional defined. Okay, so all of the operations here done within a transaction. We're simply creating a couple of accounts here with particular balances, and we are saving this into this particular cache. Okay, so we've got two accounts, one with a balance of 100, another with a balance of 200. We output here using these print lines what the actual balances are before we do any work. We apply some operations to these in terms of updating the values. So account 1 has 100 units of currency, I think it's actually dollars added to it, and the second one has 200. And then again, very straightforward, straight after that, we just output the balance. Now, if we look at the actual sort of code for the deposit here, again, we can see here that we've got some control in terms of it's pessimistic, it's repeatable read. Okay, so this is one of the valid combinations that we discussed a little bit earlier on. We're performing some updates to this, and then we are doing this commit here. Okay, and we can actually run this and have a look at the output. So it should be very straightforward. So pessimistic transactions, let me just get that up and running. Okay, just make this a little bit bigger there. Okay, so there we go. So very straightforward there. So again, you can see this simple kind of pessimistic example of how to deal with this scenario in terms of defining what sort of transactions we want, what sort of concurrency level we want, and so on. We output the balance before we do anything. It's 100 and 200 for these two accounts. We're applying some, updating these two accounts with the particular values, and then we can see the balance at the end here. And this is all done under transaction control. Now, if there was some problem and this was not completed, we would be able to get some, some errors would be printed out, and we'd be able to check those further. But this is a very straightforward and simple example. If we look at another example, so let's have a look at the deadlock detection example. Okay, next. So this one is, let me just scroll over here. Okay, so this one is a little bit more complex, because what we're doing here is we're creating 10 accounts here. Okay, so this is what this for loop is doing. And then we're just giving these accounts an initial balance. This will output the list for us. And then, as you can see here, we're creating two threads, thread 1 and thread 2. And again, we've got this piece of code here calling deposit. Again, we'll have a look at that very shortly. Now, one of these threads is traversing our list of bank accounts in reverse order. Here, for example, this is false, this is true. Okay, so we have this variable. One is starting at the top of the list and working downwards and trying to do some updates. The other one is starting at the bottom of the list and working upwards and trying to do some updates. And what will happen is there'll be a conflict at some point, because the resources required by one one thread are unlocked by the other one, and vice versa. Okay, so they'll simply a deadlock will happen. It won't be able to do anymore, and because we're going to trap that and use some exception handling code, which we have down here. Just have a look. Okay, so in this case, it will tell us that there was a deadlock detected, and using some of these capabilities that we talked about in the previous slide in terms of outputting and getting some information about what's going on in terms of helping us as far as debugging and finding out where the problem is, this will give us a bit more detailed information as to where the problem occurred, and therefore give us the opportunity to maybe work and resolve that issue fairly quickly. Now, the other thing is that in this particular example, you can see here that, again, we're using pessimistic and repeatable read. But we also have this thing here called a transaction timeout. If this value is set to 0, this won't work. The deadlock detection won't work. Okay, so we've set this to a value which I think in this particular example is 3000. There is a default that's available too, and that will give us the ability to find where the problem is. Okay, so let's have a look at this. Let's run this. Okay. And let me make this a little bit bigger here. Okay. All right. So if we just scroll up a little bit and let's have a look at this. So you can see here that it's saying accounts before deposit. Okay. So here we can see that it's created 10 accounts with an initial balance. In this case, it's sort of fairly easy, starting with account ID 1, a balance $100, and then going up to account ID 10, where the balance is 1,000. So just incrementing these in sort of $100 units. And what it's trying to do then, again, one thread is trying to deposit 100. The other thread is trying to deposit 200. And remember that these are working in different orders. So one is starting at the top of this list of accounts and trying to work down. The other one is starting at the bottom, trying to work up. And what's happened is that a deadlock's being detected. So in this case, using the messages and the exception handling that we've got, it gives us a little bit more information here that transaction 1 holds a lock, transaction 2 is waiting for a lock, transaction 2 holds a lock, transaction 1 is waiting for a lock. So there's a deadlock. I mean, the resources are tied up in the 2 threads and neither of them can get what they want. A little bit more details in terms of the actual sort of threads and what's going on. And then here, for example, we can see the specific keys where the problem has occurred at 6 and 7. So again, this is a sort of fairly simple example and sort of fairly simple output in terms of messages to tell us what's actually gone wrong and where the problem is. But this, in a production environment, very useful. We can find out exactly what's going on, where the problem is, and then again, perhaps we need to redesign our code slightly, or we need to set a different sort of level of timeout, or we think about other ways as to how we may need to do the updates for this particular type of application. Okay, so let me close this one. And let's just pull up the last example then. So this is deadlock-free transaction. Okay, so in this example, very similar to the previous one. Okay, so there's a few differences. So we'll look at those shortly. So again, what we're doing here, we're using a for loop just to create some initial accounts with some initial balances. We're printing the values out before we do any updates to those. Again, we've got 2 threads. Okay, so one thread here, reverse, is false. Okay, so this is running in natural order, and then the other one, reverse, is true. That's starting at the bottom of the list and working upwards. And then we're doing kicking off the 2 threads here, waiting for the completion, and then outputting the balance here. Now, in terms of the deposit code here, if we have a look, we can see here that we check to see what's the particular order that's being proposed, whether it's reverse is true or reverse is false. We're committing the transaction and then we're returning here. Now, the other thing is that this is done, as you can see, within a while loop, okay? So if there is some problem and something has failed, we have the opportunity to retry it. So as you can see, the exception which will be sort of caught here, if there is some problem and this commit is unable to succeed for some reason, that it's failed due to lock conflicts, okay, and it will try again. And then once this transaction is successfully completed, the code will reach the return statement. It will return it back here, and then we'll output the values. So if we run this, just have a look. Okay, it's the deadlock-free transaction. Again, just make this a little bit bigger. Okay, so there we go. So here, again, you can see we've got our 10 accounts created with the initial balances. Again, just increments of sort of $100 units there. And again, very similar in terms of what the two threads are trying to do. One is trying to deposit sort of $100, the other one $200. Now, what's happened is that conflict has been detected. That exception message has been printed. Again, it goes around through the while loop again until the transaction succeeds. So in this case, it's tried it again and it's been successful. Now, you'll notice here that what we've got here, so if we look at the initial value for account ID 1, that was $100 before the deposit. So if we look at the value sort of further down here after the deposit, we can see here that it's 400 now. So that's 100 plus the $100 from this thread plus the 200 from this one. And similarly, if we look at the other values here as well, so the last one, for example, here is $1,300. So we initially started off with a balance of 1,000 here, and it's been able to add the 100 and the 200 here as well. So that has been successfully completed. So we've been able to update this correctly. Okay, so just minimize this. And again, just remind you that you can find these code examples on Dennis Magda's GitHub account. Okay, so just look under Ignite transactions and just switch back to this. Now, I've got there's some time for some questions. We've got that available, but let me just show you this as well before we take the questions. Okay, so a couple of resources, and the basis for this presentation really are these three sort of excellent articles written by Dimitri, who is one of the sort of founders of GridGain. So these date back from 2014. So he discusses in quite a lot of detail a lot of these kind of scenarios of what happens if we have a coordinator, a primary, and a backup. The backup fails, or the primary fails, or the coordinator fails. What is the situation in what happens? How does Ignite deal with these kind of scenarios? And we've taken some of those scenarios and being able to discuss them today. So I'd highly recommend you have a look at these. Okay, so this will be part of the slides that will be distributed. But happy to take any questions, and I'll do my very best to answer them. If not, okay, we can always follow through and help answer anything subsequently.
Okay, thank you, Akmal. I just wanted to let you know that we are being joined by Principal Solution Architect Rachel Pedreschi. I grabbed her unexpectedly and pulled her into the webinar. So she's here in case there's some questions that may need some elaboration. So hello, Rachel.
Hello, everybody. Thanks for joining today.
Okay, great. So the first question is, Is the lock applied at the cache level or at the key level?
Oh, that's a good question. At the cache level, at the key level. Rachel?
Yeah, the lock would be at the key level.
Right.
So
okay. I wasn't sure if you were going to elaborate that. Okay, the next question is.
Yeah, okay. I think because at the cache level is too large. I mean, we're dealing with a lot of data that's in memory, so it's only at the individual key. So if you looked at the initial code example that I showed you, the very first one, we see that we are dealing with keys and accounts, and we're just updating those values, and we are just those particular keys are just under transaction control.
Exactly. So a good way of thinking about this, and I generally think about Ignite in most relational database principles apply to Ignite. The only difference is that it's 100% in memory, and that it does have a key value API associated with it. So a cache you can think of as a table. A key would be like a primary key or like a row or an individual entry into that table. So exactly like what Akmal said, the cache is a much too large place. If we were locking at the cache level, it'd be locking an entire table, which, hey, 1980s called and they want their relational database technology back, if that's the case.
Okay, great. So the next question is, someone's really excited. They said, great. And then how about integrations with servlet containers? For example, can I use Spring transactions and instrument it to use Ignite transaction semantics?
Oh, great question. I can check this up. I don't know unless Rachel can answer it, but I've only dealt with the level at Ignite and relational systems. So Spring is something I need to look at, but I don't know if you can assist with that one, Rachel.
So we do have a fairly robust Spring integration. Okay. Whether or not it exactly integrates with the Spring transaction or transactions integrate with Spring transactions, my assumption is yes, but I would also have to go look through the documentation for that. But I can tell you that the Spring integration is very, very well documented, and it should be a quick Google search to be able to find it.
Yeah, I think the place to look would be naturally would be the Apache website in terms of the documentation. There's also a lot of a simple Google search will bring you the website that actually contains a lot of the documentation that is written, by people like Dennis and others who maintain that for the Apache project.
Okay, next question. How can we include the Ignite transaction as part of a managed transaction of the application JMS plus Ignite?
Can you repeat that, please?
Sure. How can we include the Ignite transaction as part of a managed transaction of the application JMS plus Ignite?
Okay, so it would be with a Java messaging service, Rachel, plus Ignite.
That's probably something that I'm going to need to take as a follow-up.
Yes, I think we'll follow up.
It's a bit too complicated to try.
This is deep stuff, but great questions.
Okay, next question. How is the integration with the Ignite database? How is the integration with the Ignite database and the web console?
You mean the SQL database? Is this what we're referring to? So the web console actually gives you the ability to execute SQL queries, and it's just an interface. I mean, you can build it locally, or I think you can go to the console.gridgain.com. I think that's the website where you can create an account and use it from there. So it's a great way to have the capability to browse and look at some of the data, be able to execute SQL queries, things like that. I don't know if that's what the questioner is referring to.
Yep, there's a follow-up. He says that he tried it and it works fine with the cache, but the database state is not maintained properly.
Okay, that may be an issue then that needs to be logged in terms of the Apache project. So I think it'll be great if we can get some more details on that, what the specific problem is. But that, again, great question. Thank you for that.
Okay, the next question's for me. Will we get a copy of the presentation and a link to the video? Yes, I will send that within 48 hours. Just have to process it after the event. So yeah, that's a easy answer. Okay, so if there's any other questions, I think we have time for one more. Let me look down the list here. And I apologize if I didn't get to your question. There's quite a few, and I'm just trying to work through them. Okay, so the final question is, in which business scenario would we prefer a two-phase commit over a one-phase commit?
Okay, so I think the one-phase commit example that I gave is just a kind of it's a one-phase commit optimization. It's just in terms of the network topology, it's where we have a primary, one primary, and that primary has a backup. Okay. Now, obviously, in a cluster, you'll have more than one primary, but specifically, the example I gave was the one primary with one backup. And there, the one-phase optimization works well. You don't have to have the overhead of two-phase commit. So it's a kind of lightweight way to deal with. And I think the specific example that I was using was employees and company ID, where these are kind of co-located. So I've got some kind of affinity in terms of the employees that work for a particular company. So, for example, all GridGain employees may be held on one primary node. We may cache them all there. They are located based upon some criteria. It could be company ID, which was, I think, the example I used. And that's a fairly sort of standard, I think, set up in a lot of distributed systems where you have a primary and you have one backup. Where you may want more resiliency and you want more redundancy and more kind of, if you like, assurance that because distributed environments, many things are out of your control. And therefore, if you want to ensure that the backups are done properly, you may decide that it's better to have more than one backup. So I think the example that I gave is a fairly typical one in terms of one primary and one backup. And having the data stored on the primary in some way, because there is some association between the data, for example, just simply based on the company ID. Again, that is, I think, fairly typical of situations in the real world. And again, Rachel may have practical examples from the customers that she works with.
Not off the top of my head. A lot of my clients are happy with either, depending on what the situation is. I mean, it's the same conversation you're going to have with eventual consistency type of questions as you would with asset level consistency. Same with two-phase commit versus a single-phase commit. It just depends on what your business needs. And what's nice about Ignite is that each individual transaction can act very differently in terms of consistency and in terms of how that it commits to disk. So no specific examples that I could have off the top of my head. I'm sure if I thought about it and dig through it, I could come up with something. But
okay, well, guys and women, this brings us to the top of the hour. Thank you so much for joining us, Rachel and Akmal. Thank you so much for a great first webinar. This is the first time Akmal's actually presented a webinar for us, and it won't be the last for either of you.
It'll get better.
It was great. Thank you, everyone, for joining us today, and we hope to see you on a future webinar. Take a look at www.gridgain.com. I just posted a brand new webinar about Apache Ignite and Kubernetes, and that's actually being presented in August by a member of Rachel's team, Danny Traphagen, and she's awesome. So you'll want to attend that if that's something of interest to you. So with that said, thank you again, everyone, and have a great rest of your day. Thanks again, Akmal and Rachel.
Thank you. Thank you, Rachel.